Welcome back to our interaction on introductory sessions on spectroscopy, and in this session I wish to talk about different types of spectra and their characteristics. So, what I am basically trying to do for today's session, this session is that I will try to recall what we did in the previous sessions. Thereafter, I will try to define what exactly we mean by a spectrum, and then we will see what kind of different spectra are there, and then thereafter we will try to discuss threadbare what are the characteristics of spectrum and what are the factors that kind of contribute to the so called characteristics of spectrum, and towards the end we will try to sum up what we done today. Okay. So, let us make a beginning by recalling what we did in the previous sessions. In this introduction to spectroscopy, what we have done so far is that we started with defining what is spectroscopy and explained its scope. Thereafter, we talked about the wave and particle nature of EM radiations. In the process, we learnt about the different characteristics of EM radiation and what kind of interrelationships do they have. And then we came down to kind of an understanding of kind of recalling of nature of atoms and molecules in terms of the energy level diagrams and all. Thereafter, we explained the possible types of interaction between the radiation and matter, and towards the end of the previous session we tried to discuss about the prerequisites or the necessary conditions required for the interaction of radiation and matter to take place, because there has to be some kind of a mechanism by which the radiation and matter can interact for the spectrum to be observed. Okay. So, we defined spectroscopy to be interaction of radiation and matter. So, we have learnt about what is radiation, we have learnt about what is matter. We have also seen that when the two interact, that interaction is going to lead to some kind of spectrum. Let us now try to see what do we mean by a spectrum. What is a spectrum? I will first try to define it, then try to make you visualize what do you mean by spectrum. Now, spectrum basically is a graphical representation of the characteristics wavelengths, frequencies or wave number. You recall that they are equivalent ways of saying the same thing, because basically some kind of a light is being absorbed. So, we can that absorption can be talked about in terms of wavelength or frequency or wave number, and there are alternative ways, because for different spectroscopies we choose different kind of x axis parameter. Sometimes it is wavelength, say UV visible, it is wavelength. In some cases like IR we will be using wave number and so on and so forth. So, that kind of thing, what is being emitted, absorbed or scattered, because we know that there are three different ways by which the radiation can interact with matter, and accordingly there are different types of spectra we come across. Okay. Now, let us make a beginning by looking at a typical spectrum, and a typical spectrum will depend on how do we kind of obtain the spectrum. That is what is a kind of experimental setup. Just for sake of it, there are three broad types of that. One is an absorption spectrum, second is an emission spectrum, the third one is the scattering part of it. That basically are the consequences of the type of interaction that is taking place between radiation and matter. And this is more of experimental setup. We will talk about this experimental business or experimental setup or the instrumentation part in one of the later sessions. But for right now, what I want to talk to you about is what is an absorption spectrum, how does it look like, what does it mean to us. Let us see. Now, if I look at absorption spectrum basically is a plot of extent of absorption of radiation by the species or the molecule in particular, or maybe an atom or molecule, as a function of wavelength, frequency or wave number of the radiation being absorbed. So, when I defined spectrum in general, I talked about the possible absorption, emission or scattering. Now, since I am talking about absorption only, so I have to define that I am talking about only the absorption of radiation, other factors are taken care of. So, basically this definition comes from our earlier definition of spectrum in general. Okay. Now, having talked so much, let us have a look at one typical absorption spectrum, say a UV absorption spectrum, that is the simplest one. Say I am taking some arbitrary molecule. Now, what I want to talk about here is that how do I read into this spectrum, what does it mean? What does it mean is that on the x axis I will have wavelength here. In this case, it could be wave number, it could be frequency or whatever. That means, we defined that it is a graphical representation of some kind of an intensity here, absorption, what is the extent of absorption of radiation, and this is the kind of vibration, which radiation is being absorbed to what extent. Now, suppose I talk about say radiation at say 207 nanometer, we find that it is absorbed to a large extent because signal is very large. As against that, say radiation as 220 is absorbed to a very small extent, around 227 absorbed to a larger extent, and so on and so forth. So, basically what it means is that I am trying to graphically represent that which wavelength is absorbed to what extent. Okay, let me just elaborate a little more on this. How do we actually do this? What do we do is that we take a sample. Okay. Then what I do is I have some source of radiation here. The radiation is giving me, the source is giving me all kind of radiations. We will talk more about it in the instrumentation, but for the sake of it, now from that radiation I have some mechanism of controlling what wavelength is coming from there. That is, you are using some kind of a monochromator. When the radiation comes and falls on this, so I have, okay, let us assume that there is some kind of an instrument there which can generate some particular kind of frequency. It is same similar to what we have in case of our say radio. I can switch it on, kind of tune it to FM1, tune it to FM2, tune it to FM3. So, I can fix the frequency there. Similarly, here I am having some source, from there I can make a particular radiation, say I allow 200 nanometer to pass through, okay, and then see what happens, what comes from here. What I find is, I suppose I give certain intensity of this radiation which falls on this, I find which comes out is almost our same intensity, slightly reduced. That means 200 nanometer radiation is absorbed to small extent. I increase the wavelength to 201, 2, 3, 4, I keep on changing. This can be done with small simple computerized programs are there. That means the instrument itself has that program. I can just allow kind of instruct the computer to make different kind of wavelengths to pass through this. So, I start with 200, 1, 2, 3, keep on doing that. So, I instruct the instrument to start from 200, go to about 250 nanometers and make each radiation pass through the sample one by one. And then on this side, I will try to have some kind of a means of observing, that is some kind of detector is there to see whether radiation is coming out, what is the intensity of radiation now. Okay. So, what I find is that this detector is going to monitor, and this is essentially a trace of all that. So, what it tells me is that the radiation at 207 nanometer is absorbed to a very large extent, because its absorption is very, very large, whereas this is absorbed to a lesser extent. Or in other ways, from 200 onwards to about 240 nanometer, most of the radiations are being absorbed to various extents. And in this typical spectra, we find that there will be certain wavelengths which are absorbed to maximum extent. So, this will be called as lambda max. That is a typical ways of writing it. I will put it as lambda max 1. I mean, this is the first maxima in this spectra. Similarly, this is the minima here, this is another maxima here, because they are very characteristic of the compounds I am talking about. That means that this will be the spectrum of a given compound. Suppose I have another compound, it will have a different kind of spectra. Each compound will have its own different spectra, because that spectra will depend on what is the energy level diagram of the things. We will talk more about it as we proceed. Okay. Now, so essentially what I was trying to convey here was that something of this sort is happening. You have a sample here, you are trying to pass through number of radiations. It is just a depictive one, we do not do that way. As I just told you, we do it in a very systematic way, we pass each radiation one by one. But for sake of it, what I wanted to convey was that when I pass radiation, we are passing different radiations here, some of them are absorbed and something comes out of it. So, what is being absorbed, what is coming out, that is exactly what is meant by an absorption spectrum. We absorb, see what is being absorbed and to what extent. Okay. Now, similarly, we can have a look at a typical vibration spectrum or an IR spectra that looks something like this. Right now, there is no need to bother about what is the meaning of all this. We will talk about the nature of spectra when we talk about vibration spectroscopy. But for sake of it, what we are seeing here is that in case of UV visible spectrum was much simpler. There was only 2 big signals, maybe 3, 4, 5. So, there will be a small number of signals there. Whereas in case of IR spectrum, there are a large number of signals. Okay. So, and then this is a little complicated one, but we can still read into this, we can use this spectra to get information about the molecule we are talking about. We will talk more about it in the vibration spectroscopy. Now, similarly, let us look at one of the samples of emission spectra. Basically, I am trying to do is I want you to have a look at how does a spectrum look like, how does a UV spectrum look like, how does an IR spectrum look like, how does a fluorescence spectrum or an emission spectrum look like. Essentially, emission spectrum similar to absorption spectrum will be a plot of the extent of radiation being emitted now. In the case of absorption spectrum, we had to what extent is being absorbed. Now, we want to see in emission spectrum that the radiation is getting emitted by a sample, to what extent it is absorbed. That means, when the spectrum is coming, the radiation are being emitted. So, what radiation are being emitted and to what extent. So, that kind of a graphical representation is my emission spectrum. Let us look at in a picture. So, what you see is this red picture here, red curve here is a typical fluorescence emission spectrum. And this picture actually this tells you about the kind of radiation being absorbed. The fluorescence is a little more involved phenomenon. I will not be talking about that. So, basically what I wanted to tell you here was that I am just trying to show you a trace. It is something similar to what you have in case of absorption spectrum. That means, we are seeing that to what extent the radiation is being emitted, and this is the wavelength again. So, typically in all spectra, that x axis is going to be wavelength or some equivalent of wavelength, wave number, frequency or whatever. And on y axis, we are always going to have some measure of intensity, be it absorbance, emission, transmittance or whatever. So, the different way, that means basically a spectrum is going to be a plot. Okay. We will talk more about it when we come down to individual spectroscopies. Now, we have to understand here is the kind of spectrum I am showing you, because we are talking about molecular spectroscopy, and the spectrum I am showing you, they are the spectra which are also called a band spectra, because what you see is there are broad bands coming there. They are in contrast to atomic spectrum, because atomic spectrum, if you can recall from your earlier understanding of basic quantum mechanics, we know that atomic spectra are typical line spectra. You get characteristic lines there, but in this case here, what we are getting is we are getting broad bands. So, typically molecular spectra are band spectra. It is a characteristic of molecular spectroscopy. Why does it happen that this comes out to be band spectrum? We will talk about it little later, but let me share with you one more type of spectra. So, I have shown you how does an absorption spectrum look like, how does an emission spectrum look like, how does an IR spectrum also is absorption spectrum, and now I want to talk about a spectra of type wherein some kind of a scattering is taking place. Raman spectra is typical of that. In Raman spectrum, the spectrum looks something like this. Here again on x axis, it is slightly different here. This read it as Raman shift. I will just explain that. And on this side, it is intensity, typical of all spectrum, that this is some measure of the wavelength here, but it is not wavelength per se, it is the shift in the wavelength. This you will understand when you talk about Raman spectrum at a later stage. But basically what happens is we are presenting it, if you remember I just said that in case of Raman spectrum or in scattering, the scattered radiations are of wavelength slightly different from the radiation which is given to that. Okay. So, this is your Rayleigh scattering, which is because this 0 tells me that this is the same wavelength at which excitation was done. Okay. So, this is 488 nanometer. So, that is where it is coming. And what are you seeing here is these are the bands which are coming as that means there are radiations which are there in the scattered radiation, and they happen to have wavelengths different from the excitation wavelength here. So, they are on a lower side, they are on a higher side. So, what you are seeing here is that we are representing that in terms of what is the extent of shift here. Again, it is a kind of wavelength only. That means there is a wavelength here. So, I can even give it in absolute terms. Suppose I give it 488 here, and if I put it 488, so I can just put this number as minus 218. So, I can subtract from 488. So, I get this number here. So, that will be absolute number. Okay. So, basically as I have been telling again and again that x axis is going to be wavelength or some measure of that. Okay. Now, we just mentioned, we made a statement here that molecular spectra are typically band spectra. Let us look at the reason for that. What you see is, this again is very symbolic kind. What you are saying is that this is the ground electronic state here, this is excited state here. And what you see that in case of absorption here. What is happening that we start from, say, this is my electronic ground state, this is electronic excited state here, and you can have transition from V is equal to 0 level. From this level I can land up at V is equal to 1, V is equal to 2 or V is equal to 3 level. So, that means all these 3 radiations will be absorbed. That means I will be getting signal corresponding to these 3 delta E values, which are close by. I am just giving 3, there will be a number of them. Okay. So, there will be very closely related radiations will be absorbed. This we saw the spectrum here. So, about 203 onwards to about 218, 19, all of them were absorbed to different extent. So, here again same thing is going to happen. Similarly, we may have transitions from V is equal to 1 level landing up into same lines, but in this case the difference in energy levels will be of a different kind and they will be of different wavelength of frequency. Since a large number of radiations of varying wavelengths are being absorbed, I get a broad spectrum. That is typical of all molecular spectra. They are band spectra. That is what you get is a very closely related vibrations are being absorbed. So, you get a band spectrum. Now, okay, so now at least we are now by now we know what does the spectrum mean and how does it look like. Now, let us go a little further and see what are the characteristics of a spectrum. If I look at a spectrum, there are 3 main characteristics. One, the position. That means, when talking about a position, I am basically referring to what is my lambda max. So, at what wavelength is it coming, or if I have got a signal in IR like this, or what is the frequency for that, or what is the wave number of that signal. So, I want to locate the position. So, position could be in terms of wavelength, frequency or wave number, and this basically is a measure of the difference in the energy levels involved in the transition. That means, if I have got say one level here, another level is here, if I am making this transition, it will have certain wavelength depending on this delta E value. Suppose I am talking about second transition from this level to say this level, this at much higher delta E value, so it will come at a lower wavelength. So, basically that is the meaning of position. Second interesting and very significant characteristic of a spectrum is the intensity, which I have been telling again and again is a measure of the extent to which the absorption or emission takes place. That means, if radiation is coming, is it absorbed or not? Yes, to what extent? So, that extent is given in terms of intensity. And the third one is the width. Now, if you can just recall that I showed you 3 different kind of spectra. One was say UV spectrum, very broad one, the width was very large. Then we talked about IR spectra, there were thinner lines, thinner signals there. In Raman spectrum again they were slightly in way, somewhere midway. So, what you find is that different kind of spectra what are there, they have different kind of widths. Width also is a characteristic, we can say whether it is a sharp line or a broad line, a broad signal or a sharp signal. So, that is how do we characterize that. Okay. So, there are 3 main characteristics of a spectrum: the position, intensity and the width. Let us talk about each one of them one by one. Now, let us try to rationalize how do I talk about the position of a signal. Now, to understand that I am showing you a generalized molecular energy level diagram for a given molecule, and then see what kind of possible transitions are there. This picture I am sure that you must be familiar with. This is typically a generalized diagram which shows you the possible energy levels of a given organic molecule. What you see is there are sigma levels there, the pi level, that means this is a sigma bonding, pi bonding, and this is non-bonding, pi anti-bonding and sigma anti-bonding. There are 5 different broad types of orbitals we have in a molecule. Now, what you are saying is that in these possible levels, what are the possible transitions there? You can have n to pi star, you can have pi to pi star, you can have n to sigma star, you can have pi to sigma star, or say sigma to pi star or sigma to sigma star. So, there are the possible transitions what we can think of. Now, let me take 2 examples here. Let me say talk about pi to pi star and n to pi star. Pi to pi star is say from this is my pi level to pi star level, and this is my n level. So, this is my n to pi star level. Okay. So, what I find is that pi to pi star is of larger delta E value. That means, the energy difference between pi and pi star is larger than that of between n and pi star. If that be so, what will happen? We know that our energy is related, or the wavelength is related inversely to the energy. delta E is 1 by lambda, proportional to 1 by lambda, or vice versa. So, since energy involved is more, the pi to pi star transition will come out at lower wavelength than the n to pi star. N to pi star will come at a higher wavelength and pi to pi star will be at a lower length. So, we can say that the wavelength of absorption of pi to pi star will be less than n to pi star. Okay. So, that is basically just to see that if I have got different transitions possible in a molecule, where does each one of them come? So, that basically will be determined by, that is, what are the energy levels involved in the transition. If they are very close by, the wavelength will be large. If they are farther apart, wavelength will be less. That is how it goes. Okay. So, that is about the position of the signal. Now, intensity. Intensity is little more involved. Position is just, it depends on the energy levels involved. In case of intensity, what we see is that there are 3 factors by itself which contribute to intensity. The factors happen to be the transition probability, I will elaborate on that. Second is the population of the states from which the transition is originating, and the third one is path length of the sample. Let us again to understand intensity, let us talk about each of these factors one by one. Let me take up the transition probability first. If I look at transition probability, what does it mean? Transition probability is basically a measure of allowedness of a given transition. What it means is, if I have got 2 energy levels, say from here to here. So, the level molecule can be here or in this level. So, suppose it is in this level, if I give energy to that, is it allowed, does it happen that this molecule can get from this level to this level, whether this transition is allowed or not. This actually is a quantum mechanical concept which basically depends on the nature of the wave function for this level, nature of wave function for this level, and also the kind of perturbation, the kind of interaction we are going to talk about. So, it is a little more involved one. So, basically on a simpler level we can say, suppose the probability that the transition can take place happens to be 1. So, that is a maximum, or it could be 0. 0 means not allowed, 1 means allowed. Okay. And typically if you try to see numerically, the transition probability comes out to be anywhere between 0 to 1. If it is close to 0, we say it is forbidden. You must have come across this term, that is a forbidden transition. And if it comes closer to 1, so 0.9, 0.95 or anywhere around that, we say it is allowed. So, the transition probability, the probabilities for a given transition to take place is somewhere in between. So, that is going to determine the intensity. Let us see how does it happen. Now, look at this diagram here. So, what I am showing you here is that this is one set of energy levels here, say psi A1, psi A2, and this is my another set of energy levels, psi B1 to psi B2. I am talking about transition 1 here, a transition 2 here. What I have done is I have purposely chosen, I am just taking a hypothetical example. I have purposely chosen that the delta E values for the 2 transitions in this case and in this case happen to be equal. That means the position is going to be the same. Okay. Secondly, if I take equal concentrations of solution, that means I am trying to ensure that the concentration does not come into picture, because otherwise concentration also is the factor which determines the intensity. We will talk about that later. So, the signal corresponding to transition 1 is more intense than the that due to transition 2. So, what that means, if I say this happens to be more intense than this one, this can happen if and only if the transition probability of this transition, that means the allowedness of this happens to be more than that of this, because otherwise all of the factors have become constant. I have kept the energy to be same, I have also kept the concentration to be same. So, the two, if there is a difference, the difference can be attributed only to the allowedness of a transition, or in other words, suppose I got 2 transitions possible. If one is more allowed than the other one, this will be more intense than the other one, as simple as that. Suppose everything else being same, 2 transitions are there, if one transition is allowed to more extent, so that will show up as a more intense signal. That is the meaning of transition probability. The second factor was the population of states. Now, let us again understand this by a diagram here. Now, let us say I am taking again a hypothetical case. Let there be a transition possible from a level E1 to E3, another possibility from E2 to E3. Now, in this case, suppose there are 2 kind of transitions possible here, and what I say is that let me assume that the concentration of the 2 solutions happen to be same, and secondly let me also assume that both the transitions are allowed to same extent. So, they are fully allowed, 100% allowed. Okay. So, that is not going to matter now. So, again in these two cases also the intensity is going to be different, because the intensity, the second factor going to determine the intensity is the population of states. What it means is, now suppose there are say about 1000 molecules in this level, and suppose there are 900 molecules in this level. Again I am taking very arbitrary numbers, they are never like this, there have been trillions and trillions of molecules. So, if I have that and my transition probability is the same, let me say I just said 1, let me say assume it is allowed to 20%. What does it mean? Out of 100 molecules, 20 will be going up like this, that means 20 will absorb radiation, go up there, the intensity will be proportional to 20. Whereas in this case, since my initial population happens to be 80, the 20% of it is going to be 16. So, now only 16 molecules will be able to go up. So, this signal will be corresponding to 16 molecules, this signal will correspond to 20 molecules. That means, they will be of different intensity. That is the meaning of that, how does the population of state affects it. To put it more formally in terms of a very, very important significant equation, the population of different energy levels are given at a given temperature is governed by what is called as a Boltzmann equation. Let us understand that. Boltzmann equation reads as follows, that is n happens to be the population of upper level to population of the lower level is equal to exponential of minus delta E by kT. Let us understand each one of them. Delta E is the energy of the upper level where the transition has to go, E lower is the energy of the lower level. So, that means this difference E upper to E lower happens to be delta E, and T is the temperature in Kelvin, and small k happens to be Boltzmann constant. It is a very fundamental constant. So, what you see is that if this delta E goes up, that means I am talking about the population at different levels with respect to my ground level here. Now, let me go back to my previous picture. So, let me assume that because there are E1, E2 states, let me assume my E0 state is somewhere here. Okay? So, from this E0 state, if I try to see that from here to this level, delta E is to certain value is there. I am sorry. So, from this level, so this is some delta E is there. For this one, delta E is larger. When this delta E is larger, according to my Boltzmann equation now, if delta E happens to be larger, since it is negative exponent, the population of the level I am talking about E2 here will be lower than that of this one, which I made an assumption 180, 100 in this case, 80 in this case, I just made an arbitrary assumption. But in terms of a very fundamental equation also, we know that the population will depend on the energies of the states. This will be lesser populated than this one. So, if everything else is same, the transition which comes from here will be more intense than that comes from here. So, that is the second factor which determines the population. And third, which I have been telling again and again, is the path length of the sample. What it means is the following. Now, this is my sample here, this is my incident radiation coming with certain intensity there, and this is the radiation which is coming out, because some of the radiation has been absorbed, this is a transmitted radiation which comes out of there. Now, if I increase the path length, that means, if I instead of taking such a big cell, the quartz cell or a cuvette as it is called, if I take it slimmer one, now let me assume, okay, this is my sample compartment, okay, I am giving this radiation here. Suppose the sample happen, the radiation goes through this, passes through this whole path length, and in the process, whatever number of molecules are there, this radiation is going to interact with them. And the possibilities that it interacts with certain number of molecules and the transition that take place will depend on what is the length it passes through. Now, suppose it passes through this length, I have certain number of transitions taking place, and then we have got some intensity coming here. Now, suppose I reduce this, my path length was this much, I reduce it to just this much. If I do this, then when this radiation passes through this, it comes across very small path length. That means, it meets very few number of molecules. Accordingly, the possible transition which can take place, the possible number of molecules which can absorb this radiation becomes much less. Accordingly, the radiation which comes out will be more intense. That means, absorption will be lesser now. Okay. So, absorption will depend on what is the path length of sample. Everything else remains same, the path length of the sample also matters here. Okay. So, this effect of path length of a sample on the intensity of the spectrum can be described in terms of a very important law called as Lambert's law, which says that intensity of transmitted light decreases exponentially when the thickness of the medium through which the light is passing increases linearly. We will talk about it when we talk about the electronic spectroscopy, the applications of that. But for right now, I just want to in the passing talk about that mathematically this is given as the following, that is where P naught is the intensity of radiation which is falling on the light, falling on the sample, P is the one which is getting transmitted. So, and this happens to depend on B is the thickness of the medium, thickness, that is the path length I am talking about. Okay. So, more about it we will talk when we talk about electronic spectroscopy. Now, let me take up the third characteristic of my spectrum, that is the width of the spectral line, and this width depend on two things. One is an extrinsic factor or instrument related factor, and second is the intrinsic factor, that is one which is more pertinent here, which I want to focus on. Let us talk each one of them. Now, extrinsic factor basically is related to instrument. So, basically what happens is in the instrument you use some kind of slits, some kind of gaps from which the radiation is coming there. Now, if we typically try to make slits as narrow as possible, but even then it has some kind of a finite width. So, it allows more than one kind of radiations to pass through. This is more little technical one, but this can be improved. What we can do is since it allows a range of frequencies to pass through, if I make the slit narrower and narrower, I can control the frequencies going there. So, when I am controlling the frequencies going there, I am controlling the width of the spectrum there. Okay. But this whole thing can be improved to some extent by making that slit as narrow as possible, but we can't make it 0. Since we cannot make it infinitely small slit, so there has to be even if we do that, even if we come to the narrowest possible kind of a slit, we will find that the spectrum still has a width, and that width which no instrument can take care of, because that width is going to be there, because that width is something intrinsic to the system that no instrument can remove. Okay. So, that will be there, and that is one thing which is more pertinent here. Let us talk about the natural line, that is called as the natural line width, the intrinsic or the natural line width here, and the natural line width in turn depends on another 3 factors. The factors happen to be since I am talking about a broadness, a width, so this is called as a collisional broadening, second is called as a Doppler broadening, and third one is called as a Heisenberg broadening. Let us understand each one of them. Collision broadening, what basically happens in this is that we know that in any sample, if you take a liquid sample or a gaseous sample, molecules are in constant motion. When they are in motion, they are colliding with each other, and when they collide, suppose I am talking about one atom is there, another atom or a molecule is there, the two molecules come and collide. So, when they collide with each other, they distort each other, there is some kind of a deformation, because if we assume that this molecule happens to be a sphere, this is a soft sphere, two spheres come and collide, they distort each other's dimensions. As a consequence, what happens is, since they distort, so what happens that the energies of the external or the valence electrons or that valence orbitals, they get altered to some extent. So, as a consequence, what happens is, suppose I am talking about this transition, suppose a molecule is, there is a single molecule not undergoing any collision of any kind, then say transition takes from this level to this level, certain delta E value, certain position is there. But since the molecules are colliding, what happens is, as a matter of collision, as a consequence of collision, this level, the higher level, the outer level, that gets altered. In some cases the energy will become less, in some cases the energy will become more, in some molecules it will remain the same. Since each one of them is going to absorb, so you may have transition, suppose this is absorbing at say 100 units, you may have here a possibility that the transition at 100 units, they are there, maybe 101, 102, 99, 97. So, we find that a number of radiations are getting absorbed. So, the spectrum will be broadened. That is the meaning of collision and broadening. That means, a broadening in the spectrum is the width is coming because of the collision between the molecules. That is the first reason. And second is and primarily in addition to, I am just trying to give you an idea about that they are colliding. Basically, I am talking about electronic energy levels. Same thing happens, that this collision can also affect the rotational and vibration energy levels, and that also the spectra does become broad. Second is Doppler's broadening. I am sure that you all have heard about Doppler's effect. We will just talk about it. Now, basically what happens is, since the molecules are in constant motion, they are moving in very rapid speeds. So, what happens now, suppose I am giving some kind of a radiation. Suppose, let me assume again that this radiation is coming of say 100 units of frequency, 100 hertz. I am taking arbitrary numbers, and now this molecule is here, and this needs 100 hertz to get transition, okay, get excited over there. But what is happening is, I am giving 100 hertz here, but this molecule is going away from this. Since it is going away, so this molecule sees this 100 hertz to be different. And suppose you take another molecule, this radiation is coming at 100 hertz, this molecule is coming closer to this in a very rapid way. You know that in the Doppler effect, I am sure that you have come across that in the school physics. That is, a typical example is of a train. Suppose a train is giving a whistle, and if a train is approaching a station, the frequency is different. If a train is leaving the station, the frequency is different, and that is basically what is Doppler's effect. Now, in this case, what you are saying is the molecules are trying to either moving very rapidly towards the source, or they are going away from the source. As a consequence, there is some kind of a shift in the frequencies. Okay. As a consequence, the molecule absorbs in addition to 100 hertz, it will absorb 99, 97, 98, or maybe 102, 104. So, again some kind of a broadening is coming out. That is what is called as a Doppler's broadening, which no one can change unless we make the molecules come to rest, which will never happen. Okay. So, the frequencies will shift in both ways, to higher side as well as to lower side. Let us move further. Let us talk the third effect of causing the width of a spectrum, that is called as Heisenberg broadening. This again is a very, very fundamental effect. Now, we know that as per the Heisenberg's principle, we have talked about Heisenberg principle in terms of delta px into delta x. That means uncertainty in position and uncertainty in the momentum, they happen to be greater than or equal to h by 2 pi, h cross by 2 pi. Now, we have a similar relationship between energy and time. What we have is that delta E, that is uncertainty in energy, and delta T, uncertainty in time, they happen to be approximately equal to h by 2 pi, or about 10 to minus, or order of 10 to minus 34 joule per second. Now, if we have this, and what we are going to see as a reason for this broadening coming is, now if you look at the ground state, typically ground state we know is something which everything will try to acquire. That means, suppose anything is in ground state, will like to be there for all times to come. That means, the time spent by a species in ground state is very, very large. That means, if it is not disturbed, nothing will happen to that. So, there is no, in such a case, there will not be any uncertainty in the energy, because the delta T has become very large. So, on the other hand, the excited state, suppose a molecule has been given energy, it has gone to this level, it does not stay for long, it has very short lifetime there. So, if you got a short lifetime, it will try to come down there. So, in that case, what you find is that there is some kind of a uncertainty will come into picture in terms of the energy of that level there. So, the delta E will be equal to 10 to minus 34 divided by delta T. That means, this is the lifetime of the excited state there. If lifetime is more, this will be less. If this is less, delta E is going to be more. So, basically important here is that the excited state becomes uncertain to certain extent. Now, suppose I take again the same kind of example. Suppose this level is at say 500 units, and this level was at 600 units, delta E was 100 units. But because of the uncertainty in energy here, so this energy may not be 600, maybe 598, maybe 603, 604. So, what you find is that transitions will be there of 100 units, 98 units, 103 units, 104 units. So, as a consequence, there will be a broadening, and that is what exactly is meant by Heisenberg's broadening. Okay. So, we have seen that there are three different reasons which contribute to the broadening of, or the widening of a given spectroscopic signal. Okay, let us quickly wind up and sum up what we have done today. What we have done today is that we have defined what is a spectrum, how does it look like, and then we talked about different types of spectra. Thereafter, we outlined the characteristics of a spectrum. What are the characteristics? That is the intensity, position, intensity and the width. Thereafter, we explained the origin of each of the characteristics of spectrum and outline the significance of each of the factors affecting these. That means, what determines the intensity, what determines the position, what determines the width, and we discuss in detail about each one of them. Now, having done this, in the next session, now we will try to talk something about, because we did mention something that the spectra will depend on how do you obtain that is something about instrumentation. So, in the next session we will talk something about the spectroscopic instrumentation very broadly, because we do not have to go into details of that one, but I will try to give you some kind of a broad picture of what kind of instrumentation involved in doing spectroscopic measurements. Thank you.